All right, previously on inference, we were talking about inference for proportions. So first of all, what is inference? Inference is inferring things from data. If 50 out of 90 people did X, what does that tell us about how many people actually do X? Or how different is it from this other population where only 40 of 90 do X? The only thing changing now is what kind of data we're dealing with. Now we have quantitative data instead of qualitative data. So let's use height as an example. Previously, we'd have been able to ask what percent of people are over 6 feet. Now we're going to deal with their actual height, right? A yes/no question versus a number answer. So the way we summarize this data is different, right? Previously, we were dealing with percents. All of our data was a yes or no, and so we summarized it by like figuring out what percent were yes and what percent were no. Now we'll have a mean and a standard deviation to summarize our data. This changes the mechanics of everything we're doing, but really very little else. Remember when we talked about sampling distribution models like 2 months ago? We had a couple different models. The first one is the counts model. This is where our expected value is the sample size times the probability, and the standard deviation is square root of NPQ. And then there was the proportions model, where our expected value is the probability, and the standard deviation is square root of PQ over N. That's what we turned into like 4 different chapters. Well, there's a third one. We talked about it, but didn't go much in depth into it. Now is when we do that. The mean is, or the expected value is mu, the mean of the population. And the standard deviation will be sigma over square root of n, sigma being the standard deviation of the population. Long story short, basically what we can do is just kind of replace P with mu and square root of PQ over N with sigma over N, and we're good to go. You know the next 3 chapters. Of course, it's not going to be that simple. There are a couple of subtle nuances that we have to talk about. First is the sample size condition. Obviously, NP or NQ makes no sense in this case because we don't have a probability. We just have a standard deviation. Like, yeah, we have a mean and a standard deviation, but we don't have a probability. So basically, in order to use the normal model, we still need a large enough sample. We need a large enough sample for the central limit theorem to kick in. But it's going to be a little different. So the central limit theorem says that as the sample size increases, the sampling distribution model looks more and more normal. And the sampling distribution model is what we care about. That's the model with the mean of mu and the standard deviation of sigma over square root of n. So this will happen no matter the shape of the population, no matter the distribution of the population. The population could be normally distributed, it could be skewed distribution, it could be bimodally distributed, whatever. As the sample size gets larger, the sampling distribution model will look more and more normal. Now, this happens as n gets larger, as our sample size gets larger. How large is large enough? Well, if the underlying data is normal, n equals 1 is fine. I mean, actually n equals 2 for reasons we'll talk about in a bit. Basically, you can't estimate your standard deviation from only a sample size of 1. The problem is that we don't know the shape of the population. We're estimating that from the sample 2. And it's hard to tell what the population looks like with only a sample size of 3. So what you're going to do, you're going to make a histogram of the data from your sample. We're not trying to prove that it's normal, more like the opposite. We're trying to see if it's not normal. If we can rule out normality, then we have a pretty good idea it won't work. So with a small n, the only way to do this is look for outliers or significant skew. If it's plausibly unimodal and symmetric, you're fine. But with a sample size of 10, it's hard to tell a lot except for outliers, essentially. For a medium-sized sample, skew is bad. The small skew is okay, but like the thing is you can't really tell how much it is actually skewed population and how much it's just your sample. So if you see something that looks like it might be skew, but ignore it because it might not be skew. If it looks definitely skewed, throw it out, but if it looks small skewed, it might not actually be small skewed, it might just be your sample is bad. Well, not bad, but I mean, samples are random. And so they will do, random is as random does. For large samples and bigger than 50, almost anything works, except for extremely strong skew. Like, if your data is 90% in the leftmost bin, it's not okay. But anything else, it's probably okay because this is large enough for the central limit theorem to really start kicking in. So like examples of bad stuff like income, where your bins might be $100,000 each, and 90% of your data at least will be in that first bin. So that's something that we would throw out. That's our new sample size condition. Next up, we can't actually use the normal model either. But if our sample is small, we have to go out 4 standard deviations. So this would be a sample size of 3. We have to go out 4 standard deviations for it to seem as weird as we did with 2 standard deviations before. If our sample size is 2, we'd have to go out over 12 standard deviations because, keep in mind, these are not the actual standard deviation. This is just an estimate of the standard deviation based on 2 things, which is going to be a bad estimate. What does this mean for us? Well, basically all that changes is the mechanics. We use TCDF instead of normal CDF if we're doing it by hand. There's a new parameter, degrees of freedom. Degrees of freedom is, in this case, the sample size minus 1. Right, remember where we got standard deviation from? Our estimate of a sample standard deviation, square root of the summed deviation squared over n minus 1, it's the same n minus 1. And then on the calculator, you use a t-test or a t-interval instead of a z-test or a z-interval. So like, not really a whole lot changes in what you actually do. You just click one different button. Oh, also we have a t-score instead of a z-score. All right, on to some quick formulas and then on to the examples. All right, a 1 sample t-test. Your t-score is going to be x bar minus mu over s over square root of n. So x bar, this is the mean from the sample. Mu is the mean from the null hypothesis. And S is the standard deviation from the sample. And then there's the 1 sample t interval. We'll get x bar, the mean from the sample, plus or minus our t value, critical value, t-score, whatever, t-value, times the standard deviation. That's it. I'll see you in the examples.